Hi friends, welcome back to the course. So we will continue from where we left off actually. Today I'm going to explain you when we started. We assumed the excitation to be assuming a form of f0 cos omega t. Then we had a really hard time with a lot of after performing a lot of mathematical manipulations. We arrived at an expression for x of t. But just think of the case where we can actually represent the excitation using exponential functions like this. There is a definite advantage of expressing excitations in using exponential functions. So if you're just wondering how this excitation, how we can appreciate this excitation physically, we can actually we have actually learned in our high school physics that e raised I omega t will be cos omega t plus I sin omega t. So if your excitation is given as f0 cos omega t, then you can always write your excitation as f of t is, let's say, it is a real part of my f0 I omega t. Now, again, another class of harmonic excitations will be happening. If f0 sin omega t is the excitation, then we can write it as imaginary part of f0 e raised I omega t. So, we will, by using this kind of a notation, we can effectively represent all harmonic excitations. Okay, make sense? Now, we know f0 is e raised I omega t, so from the same concepts that I discussed last time, I can assume my response to be having a shape like this, where x is the amplitude and e raised I omega t capturing my variation or with respect to time. So you want to pay attention that this omega is same as this omega. So that again comes from the last lecture's assumption. Then x dot can be defined like this, x double dot can be defined like this. And always keep in mind that x can be a complex number as well. There is no restriction that x should be a scalar or a real number. Okay. Now, once we, let's say now I want to plug this equation into the differential equation that I am having here. So this is the differential equation we are having, ms double dot plus cx dot plus kx equal to f0 e raised I omega t. And in the last lecture I explained we can actually reduce the differential equation, or we can modify the coefficient of each of the terms in the differential equation, dividing the whole equation by m throughout. Now, once we do the substitution, then we will arrive here. So it is pretty simple algebra, nothing else. Now, x can be written as like this. X is one more thing. X, before that we have to make note of the fact that x was represented like this, e raised I omega t. So once we substitute this x over here, then this e raised I omega t and this e raised omega t will cancel each other. So we are only left with capital X times omega n square minus omega square plus I2 zeta omega n is equal to delta static omega n square. Make sense? Where x was the amplitude of my response. Now x will be delta static times omega n square divided by omega n square minus omega square plus I2 zeta omega n. Make sense? Now, from a simple mathematical manipulation like dividing the whole numerator and denominator by omega n square, we can further simplify the equation. So now x can be written as x is equal to my delta static times 1 divided by r square, where r is my frequency ratio, plus I divided by 2 zeta r. Now let's say I'm calling this new term by g of I omega. So this is called the frequency response of, this is called frequency response. We will talk about this in detail, so for the time being just assume that this is known as the frequency response. Now why it is called as frequency response? Because that actually tells us how the amplitude of my excitation will vary with respect to the frequency, because my frequency, excitation frequency, is there in this term. So this frequency response will actually help us, or it will tell us how my amplitude of the response is varying with respect to the excitation frequency. Now, and moreover, you can think this modulus of g of I omega as the value by which now x is the amplitude of our system when it is undergoing an harmonic excitation, whereas delta static was the amplitude or the deflection in our system when the force was time independent, or it was independent in the sense it was not harmonic. When we applied a constant force, or time independent or constant force, that was this was the response, this was the magnitude about by which the system got deflected. So magnitude of g of I omega will tell me how much it is getting amplified, how much, by what amount my response is getting amplified. So in that regard, this magnitude of this quantity is also known as magnification factor. So that tells you how much the response get magnified. Make sense? Going ahead, let's now combine everything and write an expression for my x. So if I write a final expression for my x, then it will be look like something like this. My little x of t was initially capital X e raised I omega t. Then after doing a lot of mathematical manipulations, we came here and we told it will be delta static times the g of I omega e raised I omega t. Make sense? So this is the response. This is the response we were looking for, where g of I omega was 1 divided by 1 minus r square plus I2 zeta r. Now if we multiply the numerator and the denominator with the complex conjugate, then we will arrive at a more useful relation, where we can write this as 1 minus r square whole square plus 2 zeta r whole square, this getting multiplied, and 1 minus r square plus minus I 2 zeta r. Make sense? Now this tells us a few things. What is that? So if we want to calculate the phase of this particular quantity, because let's say we want to multiply these two terms together, then every complex number can be represented as in exponential form. So every a plus ib can be represented in the form r e raised I theta. Very useful formulas. So keep if this is a plus ib, then this can be represented as r e raised I theta, where your r is given by root of a square plus b square. That effectively means the magnitude of your complex number. Then I theta is given by tan inverse B by A, or the phase. Similarly, if we apply the same concept here, so G of I omega can be represented as, let's say, modulus of G of I omega. That means the absolute value, this will be a scalar when I'm taking a modulus, e raised minus I phi. I'm writing it like this. See, I'm writing explicitly putting a minus phi here because I will define phi accordingly. And now I will define phi like this. I will define phi as such. Phi is equal to tan inverse of 2 zeta r divided by 1 minus r square. Okay, so this is my phi, and modulus of G of I omega will be simple algebra. If you do that, it will be 1 divided by root of 1 minus r square whole square plus 2 zeta r whole square. So you have seen a lot of maths. For the next 2 minutes, I'm going to I'm putting everything in a nutshell, and I will show you one slide and then we will sum up this particular video. So let's summarize whatever we have told. So we started off by saying that we have a system, single degree of freedom system, which is undergoing an excitation given by this. Now finally we assumed the response like this, then we found out a value for x, then we talked about the frequency response, then we talked about the magnification factor. So the final expression for your response goes like this. This is your static deflection, this is the magnitude of your frequency response. This tells you how it is varying with respect to time, this particular term. The key thing to observe, it is having a phase difference, it is lagging behind the amount phi, where phi is given by this expression. This is completely known. These are all the functions of your excitation frequency and your system parameters K, C and M. Similarly, magnification factor is given like this. Now the final point is that if your excitation is cos omega t, then your excitation can be written as the real part of f0 I omega t. Similarly, the response can also be written as, if it is cos omega t, then x of t against f0 cos omega t will be real part of your x of t. This, let's say when your f0 is cos omega t, this is for that particular case. That means delta static real part, this is a real thing, this is a real thing. So it will be delta static modulus of your G of I omega. What will be the real part? It will be cos of omega t minus. Now compare what final result we got in the last videos also. This was the same expression. So doesn't matter whether your excitation is cos omega t or sin omega t. Using this technique, we can easily find its response. Now let's say if f0 is sin omega t, if the excitation is varying like f0 cos omega t, then the corresponding response, instead of here taking a real part, let's take imaginary part of x of t, which will be delta static modulus of the G of I omega term. Here instead of cos, just put a sin. So introducing the excitation or expressing the excitation using exponential functions makes life a lot easier. Thanks for watching.